Hello all of you, welcome to the third lecture on the course Analysis and Modeling in Chemical Engineering. In this lecture, I will talk about systems and subsystems. There are three kinds of or types of modeling, and I will take an example of the Spring-Dashpot system. So, just to quickly recap, we have so far discussed in this course what chemical engineers do and what do we mean by modeling, right. So, I gave an example of a process which may have an input and output, and the key thing is that the output, it has to be a function of the input, which I called the actual response of the process. And then we can build a model and we can solve it and we can get not exactly the same response, but a prediction of that response. Let me call as some other function of the input, right. And we say that the model is good enough if that prediction, whatever it has, is within an acceptable error of the actual behavior of the system, right. Okay. So, now let us come to another aspect of this course, that is, how do we choose where exactly I have to apply my model. So, we typically say that we are modeling a particular system. So, what exactly is a system, right? So, strictly speaking, we talk in thermodynamics in general as we have a system and the system is present in a surrounding, and if we think about system and surrounding together, they make up this entire universe, right. Typically, we don't care about the entire universe as strictly. Let us say I am boiling water in a kitchen, then the universe or surrounding for that is probably the kitchen or nearby house, right, not anything more than that. But nonetheless, strictly speaking, we say that the surrounding and the system make up this entire universe, right. And of course, further surroundings are typically not important for anything we care about in the model. But nonetheless, if I have to give a strict definition, then I can say that system is a part of the universe with a well defined boundary. Whenever we define a system, we define a boundary. Of course, it can be an open system and it can exchange mass and all that, but nonetheless, it is still having a boundary, right. So, a system must have a well defined boundary. The boundary may move, that is also fine. The boundary may be open, it can be a closed system or an open system, it can have a movable boundary or a fixed boundary. All of these are possible, but it has to have a defined boundary. And finally, it is typically composed of a set of parts which I refer as subsystems. The system is composed of smaller subsystems which are basically a part of the system, right. So, you can think about a system as some of the subsystems or the parts that constitute it and how those parts are interconnected. Let us say, for example, I think about a car. The subsystems of the car is the wheels, the seat, the engine and all that, right. But just the wheels and the seats do not make up a car. We have to see how to put them together, right. Then only we make a car, right. So, a car is of course composed of the wheels and the seats and the engines, but what is also important is how it is connected together, right. So, this exercise of dividing a system into subsystems and figuring out how it is interconnected is what I mean by analysis in this particular course. Again, strictly speaking, analysis typically means breaking down a system into smaller subsystems as much we can, but I will use a general definition in this course, that is, analysis for us will involve the choice of a system and breaking into subsystems wherever it is needed. That is called the approach of reduction, but keeping in mind the interconnectivity between different subsystems, and I will take examples of that. Okay. So, let us think about this particular system I am showing, a chemical engineering flow sheet. So, we have some feed which is coming into a mixer that is labeled number 1 equipment, and that is then going into a reactor. There is some chemical reaction happening here, but that is not under purview of this, right. And then it goes into a separator. You want to separate out the desired product and undesired product. Let us say this is my desired product, then the undesired product I may basically want to recycle back for whatever reason, or at least I want to separate the unreacted reactants and put them back in the reactor, right? That is called the recycle, right? So you can have some kind of a recycle stream, or you may not have it, and in this case we also have a purge stream, right? So if you think about this particular system, it has four subsystems: this mixer, the reactor, the separator, and finally a splitter that separates the recycle stream, that is here, with the purge stream, right? But then just these four together do not make it up. It is also important how they are connected together, right? And the way I have drawn it here may look different from the flow sheet which I have drawn here, but it is showing the same connections if you look carefully. For example, 1 is connected to 4. There is a stream going from 4 to 1, and that is also coming here. There is a stream going from 1 to 2, and there is a stream going from 2 to 3, that is also coming here. So, this diagram, which I will later on discuss in this course as graphs, do capture the essence of how the subsystems are connected together. So, when we think about a system, we think about the subsystems making it up and how they are connected together. The reason why the interconnectivity is important is as we change it, the system itself become different, right? For example, in this case, I am showing you two systems which have the same subsystems as earlier. The one is still a mixer, 2 is still a reactor, 3 is still a separator, and 4 is a splitter, but they are connected differently. And clearly you can imagine that these two things will behave very differently. Why here? Why in this case? Because in this case the reactor is followed by the separator. Whatever reaction product is there, that I am separating, the desired product is going out, and the undesired product and unreacted reactants I am basically recycling or purging in here. In this case, the mixer and separator are coming together. That is pretty much nonsensical, because the reactor is standing isolated alone, and I am not separating the products from the reactor, right. So, the flow sheet on the right, this particular flow sheet is not serving the same purpose as this flow sheet. In this case, we had a reactor followed by the separator. So, we can separate out the desired and undesired product. In another case, none of that is happening, and the reason why this behavior changed is not because the change in subsystems, both have same subsystems, but the interconnectivity in the two cases are very different, right. So, I want to bring home the point that a system is of course defined by the subsystems that dictate what it is doing, but also how they are connected together, and we will take both these considerations whenever we are doing a model in this course. So, what are the types in which we can do modeling, right? So, broadly speaking, there are three kinds of model we will deal with. The first model, which we will deal a lot, are these fundamental models. Let us say, when we talk about this Newton's law of gravity, which we discussed in the earlier class, F equal to mg, that is based on an accepted theory or something that has been there for a long time. People have accepted that as a fact. That is the kind of thing that will come under a fundamental model, right. So, when I am using, let us say, Newton's laws of motion, or when I am using the laws of thermodynamics, I am basically making up a fundamental model. On the other hand, there is a whole class of model called empirical models that is not based on accepted theories. What is happening there is we are using experimental data or observations that I am taking on to make up equations, mathematical equations that describe those kind of experiments. Let us say, for example, I am doing some kind of a fit. I do some experimental measurement of some property y versus some property x, and experiments give me some data, and then after looking at this, I see that it probably can be fitted by this kind of a function, that is a quadratic function. And if I do this kind of a fit, it does have a mathematical form, but it is not coming from any fundamental theory. It is purely empirical in nature, right. And therefore, it is limited to the experiment that I have done. it cannot be applied for some other system that is not same as this experiment, because whatever experiment that I am doing, I am fitting the model only to that experiment, right. On the other hand, the theories are quite general. Every object on the earth will follow F equal to mg in the same way, but that is not true in the empirical models. The third kind of models, which I will use relatively lesser in this course, is the models by analogy. Here, we do not know about this system, but I know about some other system that does not look like this system necessarily, but behaves similarly. And I will give examples of that. Another system that does not look like this system necessarily, it may be a very different system in a different context, but the behavior of that system is similar to this particular system. And when I say behavior, this system will have certain variables, that system will have certain variables, those variables can be different, but then I can set up some kind of a mapping between those variables in this system with those variables in the other system, right. And I will take an example to demonstrate this point, right, in the next class. But this is a third category of model. I do not know how to model this, but the system behavior looks like something which I can model. So, therefore, I will use that model, develop analogy to use this particular model. So, I will talk about these three models quite a bit in this course, but focusing more on the fundamental models. So, I will take one of the simple examples, not really again from chemical engineering, something that you may have already had in the high school, something similar to that, right. And I will develop a fundamental model for this case, then I will also develop an empirical model for this case, and finally, we will develop a modeling by analogy for this particular case. So, what is happening here is there is a block of mass m that you see here. This block is hanging on the wall, supported by a spring of stiffness constant K and a dashpot. If you have never heard of dashpot, think of it as a bucket containing a viscous liquid, right. So, a viscous liquid will provide some resistance to the flow, right. So, therefore, it offers some resistance in the system, right. So, there is a dashpot of certain viscosity mu, right, and this block, which is supported by the spring and the dashpot, is being pulled down with a force Fet that can be a function of time. This is an external force which I am applying, and let us say at time t equal to 0, it was somewhere over here and no force was being applied, and I started applying a force, and now the block will go down, and therefore, there is going to be a downward displacement x as a function of time as I am applying external force Fe as a function of time, right. So, I want to model how this displacement from some reference, that is the dotted line here, is changing as a function of the force, right. So, going back to our example of the process, you can imagine that the input in this case is the force which I am applying, that is what I am kind of controlling. I am applying a force on the block, and the output in this case is the displacement which I am getting here, right. And now you can clearly see that what will it depend on, even if we do not know any physics of this system, we should say that at least whatever function we are going to obtain relating the displacement with the external force must be depending on the mass of the block, that is a variable in the system, the stiffness and the viscosity, mass, stiffness and the viscosity m, k, mu, at least should be the three model parameters that should affect the system, and my models should basically account for at least these. If not other disturbance variables, it is fine, but at least these three variables must be accounted for in the model. So, now in this particular case, we can develop a fundamental model at least to a certain extent, beginning with Newton's laws of motion, and that is quite well known to us, right. So, we know that the force on an object, in this case the object is the block of mass m, is equal to mass times the acceleration of that object, and the mass times acceleration I can also write as mass times second derivative of x, because first derivative of x with time dx by dt is my velocity, and d2x by dt square, which is x double dot, is my acceleration. right. So, this is my M A in my F equal to M A, and what is the force? There is an external force that I am applying here. There is a force because of the spring that is trying to pull it up. Spring will resist the displacement in the downward direction. Spring will try to pull it up, right. And there is going to be also a force because of dashpot. There is a viscous liquid, it resists flow. If I pull the block down, the viscous dashpot will also try to pull it up, right. So, there are these three forces. At least the first one, Fe, is my input parameter. The other ones, the spring and the dashpot, they depend on the K and mu respectively, right. So, now although I just called it a fundamental model, now I am going to use two empirical equations. It is well accepted in the literature, but nonetheless it is empirical in the sense that we cannot, I would say, derive it from first principles, or it is not generally valid, right. One of that is the spring force is given as minus of K into X, right. Why it is not generally valid is not very difficult to see. If I start pulling this spring, in the beginning, yes, the force is increasing as the displacement increases, but if I keep on doing that forever and forever, what I will have at certain point is the spring is going to break and then the force goes to 0, right. So, clearly F equal to minus Kx is not valid when the displacement is very large. In fact, it is only valid when the displacement is very, very small, right. So, this particular law, what is called the Hooke's law, is generally used, but it is true only for very small displacements of the spring. Similarly, for the dashpot, we have the relation minus mu into x dot, right. Remember, we know that the stress is given as viscosity into gamma dot for Newtonian liquid. Gamma dot is the shear rate. So, shear rate is something similar to the velocity in our case, right, and the velocity is given by x dot. So, x dot is my dx by dt, right, and both of these are negative. Both of these are going to resist the displacement. So, both are acting basically in the upward direction. We have defined x to be positive in the downward direction, the upward direction is the negative direction, right. So, we can basically use this empirical equations within a fundamental model, but it is kind of an accepted theory. It is not like totally empirical. We are not doing any experiment as such, but the equation itself has been derived by empirical means. Okay. So, if I plug these things in, basically I will get an equation something like this, a second order equation, m d2x by dt square mx double dot plus mu dx by dt mu x dot plus kx is equal to Fe. And now we require initial conditions in order to solve this ordinary differential equation. It is a second order ordinary differential equation. So, we require two initial conditions, and it is not very difficult to define. I have said at t equal to 0, we were at x equal to 0. So, we start from this point, and at t equal to 0, I start applying the force. So, before that, we can imagine that the block was there in probably a condition of equilibrium. That means, it was not moving to begin with. It started to move only when I applied the force, right. So, I can also imagine that the velocity x dot at time 0 was also 0. So, the position at time 0 was 0 and the velocity at time 0 was also 0. So, if I use these two initial conditions, in fact, I can solve it. And you see here a rather complicated looking equation. I will upload the Mathematica notebook in order that I used to solve it, right. It is not very important for you to learn Mathematica and figure out this particular solution, but if you are interested, you can use that, right. But I can still bring home the points which I want to bring home here, right. So, we get some complicated equation which I am trying to solve this equation whatever I showed earlier, and you see that the behavior of a system will of course depend on the model parameters. So, in this case, I am doing it for a given choice of k, mu and Fe. Fe was time dependent in my model, but I am keeping it constant just for the sake of example, and I am changing the mass of the block, right. And you see, for m equal to 1, we have a red line, and the system goes up and kind of stabilizes. There is not much oscillation. For m equal to 5, there are high oscillations, and m equal to 10, there are probably more oscillations. Here I am plotting the xt versus t in this plot, right? Why it is happening? Think about it. This first term is my mx double dot. The other terms are something like kx plus mu x dot. It is this second order term that is typically known to give rise to oscillations, right? If you think about the equation of a wave, you will get a second order equation, right? So whenever we have a second order differential equation, it is likely that it will give you oscillation. First order equations will not probably give you oscillations, right? So therefore, if I am increasing the magnitude of this fm, I am basically getting more and more oscillatory behavior. For small values of m, the oscillations are very less. I can go ahead and do it for different values of k, keeping the other parameters constant. And now you see that in this case, the oscillations are not changing by great deal, but the final x value where the system is going is changing. Again, that is not very difficult to see. If my spring was very stiff, the block cannot be moved too much down because there is a high restoring force. On the other hand, if my spring is more flexible, then I can pull it more, right? So for k equal to 1, when the spring is more flexible, I can go for larger displacement of the block. But for k equal to 10, when we have a stiff spring, we can go for only a smaller deformation. Finally, we can also vary the parameter mu, that is the viscosity. And again, we see there that when mu equal to 0.1, in that case we have high degree of oscillations. For mu equal to 1, there is much lesser, and for mu equal to 10, it is pretty much following some kind of an exponential behavior, right? In physics, this is called a damping effect, right? So as we increase the viscosity, there is more and more damping of the oscillations. So a dashpot works efficiently in deciding the damping of oscillations. Higher value of mu will basically curtail the oscillations. Higher value of k will make the spring more stiff, and it will reduce the final displacement of that spring. You see here I am changing mu, but the final position is more or less the same x. So the final x is not changing. What is changing is the magnitude of the oscillation, right? So k dictates the magnitude of the displacement, and mu dictates the magnitude of the oscillations or the damping of the system. Okay, we can go ahead and look at the effect of Fe, and it is quite expected. If I go from Fe equal to 1 to 5 to 10, more force should mean more displacement, right? So this is Fe equal to 1, there is less force, so therefore we have less displacement, and this is Fe equal to 10, there is more force, so this is higher displacement, right? So we can analyze the system behavior if we have the full solution of the system, right? But then there is an alternate way of looking at it without doing the full solution in Mathematica. And in order to demonstrate this alternate way, I will take one more step here and find the expressions of x dot and x double dot, right? So we already have the solution in Mathematica. So I take a derivative of that. Again, it is possible in Mathematica, and you don't have to really learn it, but if you're interested, I will provide the notebooks. And the second derivative is given by this, some complicated expression. But what comes out of this is how this x dot and x double dot, which I am showing as, so this is same as x dot and this is same as x double dot, right? I am showing in here is how it is changing with time, right? So what you see here is, if I look at the displacement, it starts from 0 and it ends somewhere here, right? And it slowly increases, the displacement will increase. There is some oscillation, but then it eventually settles at a final value, right? If I look at the velocity, the x prime or x dot, it picks up. So initially there is an increase in the velocity. The block was stationary to begin with. The velocity will increase, and then it will increase to a point of maximum, and then it will start to decrease, but remain in the downward direction. Positive velocity means downward direction, but there will be a point where the velocity will start becoming negative. So the block will start moving up. That is what I mean by the oscillation. So the block starts here. It starts from a zero velocity, but the velocity picks up, velocity keeps on increasing. Eventually, the velocity starts to decrease and goes to zero. And once it goes to zero, now the block may start going up. That is my characteristic of the beginning of the oscillation, right? And then it does that for a while, and again the velocity goes back to zero, and these oscillations will eventually damp because of the dashpot, and eventually the velocity goes to zero and we reach a new equilibrium that is defined by this particular displacement x. And finally, if I look at the acceleration, unlike the x and x dot, the position and velocity, to begin with we did have a positive acceleration because f equal to ma. As soon as I start applying this force, I started having an acceleration because of that particular force being applied, right. So at time t equal to 0, the position was 0, velocity was 0, but the acceleration was positive, right. And acceleration also decreases as it is going down. Eventually acceleration also becomes 0, pretty much the same position where the velocity peaks, right. And after that the velocity start to decrease, so acceleration has to be negative, and eventually it will again go to 0, again we have oscillations, and at the end when the block finally reaches the new equilibrium, acceleration also goes to 0, right. So if we can develop this kind of an intuition without solving the equation, and maybe we can, because whatever logic I gave why acceleration has to be positive to begin with, we can do without solving this detailed equation, because in the very beginning the block was stationary, right. So therefore there was, the position was 0, that is my reference, there was no velocity, but since I start pulling it, I have f equal to ma. So as soon as I start pulling it, I am going to have certain acceleration, right. So if I can have this kind of an intuition, then we can analyze the system behavior without actually solving the full equation, and we can solve under certain limits, and this will really help us analyze the system without doing all this math. And this kind of an analysis I will do quite a bit in other examples as well, but let us first do for this this simpler example, right. So let us see the behavior at a very small time. In the very beginning, the position, even if it is falling down, the position is more or less close to my initial position, so x is close to 0, and velocity is picking up, but still it is close to 0. So in the very beginning only the acceleration is high, it is positive, right. So therefore we can approximate this entire equation by only the first term on the left hand side, because the other terms, they have not started to work yet. The system was in equilibrium, I am pulling it down, the spring force will increase if I pull it a whole lot, but if I am just there, the spring force is much lesser. The dashpot will also come into play once I start pulling it, once I pull it a lot more, but in the beginning it is small, x is 0, x dot is 0. So the spring force and the dashpot force, these are quite small to begin with. So therefore I can approximate this equation, this entire equation, by only the first term, and that is easier to solve without doing all the mathematica, and we can solve and we can get an estimate that my x is going like something like fe by 2m t square, quadratic equation, right. And if I do that, I can still estimate the initial position and initial velocity and how it is changing with time, right. So what I am doing here is I am showing this dashed lines. For the velocity, the green dashed line, and this bold line is what I get from the full solution. For a small time, both are pretty much the same. Similarly, for x, the small line and this bold line and dashed line, both of them are pretty much similar. And at the very beginning, the acceleration is also same. Of course, in this model, in this simplified model, the acceleration remains constant, but in our case, acceleration will decrease. But if I am looking at the behavior at very small times, this is what the system is going to have, right. Now, the second thing we know purely from intuition is as the block is going down, there will be a point when the block will stop accelerating, because if you cannot keep on doing it, there is a spring that will eventually start to resist a whole lot, and there will be a point where acceleration should go to 0. I am not doing it by solving that full equation, I am doing it purely by intuition. In that limit, the first term will be negligible in this equation, and I will keep only that second and third term. And after that, what is going to happen? After that, acceleration should become negative, because we began with positive acceleration, right? The velocity went to a maximum. Now the velocity should start to decrease. So acceleration should become negative. That will give me something like this. And finally, if I just look at the system for a long enough time, then finally the block has to stop somewhere. And once it stops, the acceleration goes to 0, the velocity goes to 0. So only the last term in this equation is important. So we get this particular equation only, and I can find the equation for the new equilibrium, right, which I am showing by this particular line there, that is still predicting the final equilibrium quite precisely. So this dotted line again is what I get from this equation, and I have not really solved the full equation, but still I can get the limiting behavior by simply analyzing and dropping terms from this particular equation, right. This is kind of a mathematical analysis. We are looking at the system behavior under limits. Of course, we can always go and put it in mathematical software and solve it, but this kind of an intuition is really helpful because it does not cost computational power, but also it gives an understanding of the system behavior, why the system is behaving in the way it is behaving, and things like that. So, with that, I want to conclude this lecture. So, I have taken an example of a Spring-Dashpot system, and I demonstrated a fundamental model for this system. I told you how we can analyze the system behavior. In the next class, we will look at the same system, but will develop the models which are empirical in nature and which are developed by analogy. So, with that, I want to conclude here. Thank you so much.